Welcome to this RSET online session. I am Dr. Rinku Jacob from the Department of Basic Sciences and Humanities, Rajagiri School of Engineering and Technology. The topic of my lecture for today is Photonics, and this is the third part of my lecture series on this topic. This topic is from the second part of Module 5 in the Engineering Physics syllabus for first year engineering students of Circuit branch as per the KTU syllabus 2019. These are the topics I plan to discuss in this session. These are some of the questions taken from the previous university question paper related to the topic photonics. Now we move on to the next important topic, that is fiber optics. Optical fiber is a very thin cylindrical shaped transparent dielectric or non-conducting waveguide that transmits light along its axis by the process of total internal reflection. The fiber consists of a core surrounded by a cladding layer, both of which are made of dielectric materials. To confine the optical signal in the core by the phenomenon of total internal reflection, the refractive index of the core must be greater than that of the cladding. The principle behind the working of an optical fiber is total internal reflection. When light traveling in an optically denser medium hits a boundary or interface at an angle denoted by theta, which is greater than the critical angle denoted by theta c of the boundary, then the light is completely reflected back into the denser medium. This is called as total internal reflection. The figure shows the total internal reflection condition in case of light traveling from water to air. This effect is used in optical fibers to confine the light in the core. The light travels through the fiber core, bouncing back and forth of the boundary between the core and the cladding. But for the light to strike the boundary with angle greater than the critical angle, the light should enter the fiber only within a certain range of angles, so that the light can travel through the fiber without any leakage. This range of angles are called as acceptance cone. This will be discussed in detail later. Now we classify the optical fibers into two types. One is step index fiber and the other is graded index fiber. First we discuss about the step index fiber. Let the refractive index of the core be N1 and that of cladding be N2 of the optical fiber. Now we make a profile of the refractive index of the core. For that, first we take a look of the cross section of the optical fiber. Here the central dark blue region is the core and the outer light shaded region is the cladding. Outside the cladding, let it be air. Now we place the axis to find the variation of refractive index as we move from the center of an optical fiber towards the cladding and then to air on both sides. The vertical axis shows the refractive index by n and horizontal shows the distance r from the center of an optical fiber. This will give the profile of the refractive index. If the optical fiber is having a constant refractive index throughout the core, then when we plot the profile for the core, we get a straight line parallel to horizontal axis as shown here. Now as we move again outwards, the refractive index suddenly decreases to the refractive index of the cladding at the interface as shown in the figure. Then as we move again outward, the refractive index is same throughout the cladding. So again we get a straight line parallel to the horizontal axis. Now as we move again outwards, the refractive index decreases at the cladding and air interface to unity, as the refractive index of air is unity. That is marked as unity in the graph. Now as we move again outwards, then the refractive index is same as unity. It is shown as dotted line. So the variation with distance or generally the profile of the index looks like a step. So if an optical fiber is having this type of profile for the refractive index, then it is called as step index fiber. Now these are the properties of step index fiber that we have already discussed. When the light enters through one phase of a multimode step index fiber, undergoes repeated total internal reflections at the core cladding interface and proceed forward. Here, before and after reflections, the light travels in straight line as the refractive index of the core is uniform throughout the core. Next, we move on to the second type of optic fiber, that is graded index fiber. As you can see in the figure to the right, multimode graded index fibers have a core made of very thin layers of transparent material of gradually decreasing refractive index. The core is surrounded by a cladding made of material having lower refractive index compared to the core and which is constant throughout the entire cladding. So, when we plot the refractive index profile, at the center of the core, the refractive index is maximum. And as we move outwards towards the cladding, the refractive index gradually decreases as shown in the figure. When it reaches the core cladding interface, the refractive index becomes that of cladding. Now as we move through the cladding towards the cladding air interface, the refractive index is constant, so we get a straight line parallel to the horizontal axis, and finally decreases to unity at cladding air interface, which is the refractive index of air. So graded index fiber is an optical fiber which is having this type of profile. So when you send the incident light through one end of the core, it undergoes a gradual bending towards the axis and finally reflected back at the core cladding interface. This is because as the light moves away from the core to the cladding, at each point away from the axis of the core, the refractive index gradually decreases, which is equivalent for the light to travel from one medium to another. So there will be bending away from its normal path. For a comparison, let us take a look at the figure shown here. In the top figure, we see the path of light traveling through a multimode step index fiber, and in bottom figure, it shows the path of light in multimode graded index fiber. Now we move on to the next topic, that is numerical aperture. As we discussed earlier, all the light that enters the optic fiber will not undergo total internal reflection. For the light to strike the boundary with an angle greater than the critical angle, the light should enter the fiber only within a certain range of angles. This range of angles are called as acceptance cone. So numerical aperture of an optical fiber is defined as the measure of its light gathering capacity. It is equal to the sine of the maximum value of the acceptance angle. So numerical aperture is equal to sine of maximum acceptance angle. Alpha m denotes the maximum value of acceptance angle. If we send light at an angle greater than this maximum value of acceptance angle, the light will not undergo total internal reflection inside the core of the optic fiber, and it will leak out of the core. Now we start the derivation of the equation for numerical aperture of a multi-mode step index optic fiber in terms of the optic fiber material parameters, that is refractive indices of the core, cladding and the surrounding medium of the optic fiber. For that, first we take an optic fiber as shown in the figure. N1 and N2 are the refractive indices of the core and the cladding respectively. N0 is the refractive index of the surrounding medium where the optic fiber is placed. The red line indicates the ray that is incident at one end face of the optic fiber, which is an interface between surrounding medium and the core of the optic fiber. This ray is coming from a medium of refractive index N0 to the core of the optic fiber, which is having a refractive index N1. So by drawing a normal to the interface, we mark the incidence angle to be as alpha, and this is called as acceptance angle in the optic fiber. This ray is transmitted into the core and meets at the core cladding interface, producing an angle theta with the normal to the core cladding interface. In terms of this angle theta, the angle of refraction produced when the incident light enters the core from the surrounding medium is 90 minus theta. It is shown in the figure. Now applying the Snell's law at the first interface, that is the interface formed due to the surrounding medium and the core of the optic fiber. That is relative refractive index N01 equal to sine alpha divided by sine 90 minus theta. The left side of the equation can be expressed as the ratio between the refractive index of the medium to which the light is traveling to refractive index of the medium from which the light is coming. Here the light is coming from the surrounding medium, which is having a refractive index N0 and traveling to the core of the optic fiber, which is having refractive index N1. Now we write sine 90 minus theta as cos theta in the denominator on the right side of the equation. Now on cross multiplying we get N1 cos theta equal to N0 sin alpha. Now let us look back to the figure. If we increase the value of acceptance angle alpha, then the angle theta produced at the core cladding interface will also increase. Below a particular value of acceptance angle alpha, the angle theta will become greater than the critical angle for the core cladding interface, which is essential for the total internal reflection to take place. Now if we send the light at an angle of acceptance so that the angle theta will be equal to the critical angle theta c, the light ray after hitting the core cladding interface just graze over the core cladding interface without leaking from the core, and so that the light can be guided by the optic fiber. This particular value of acceptance angle is called as maximum acceptance angle, which is denoted by alpha m. So if we send any light at an angle greater than the maximum acceptance angle, the angle theta will be less than the critical angle. So the light will leak out of the core. So transmission of light through the optic fiber will not be possible. So if we take the limiting condition, that is when alpha becomes equal to maximum acceptance angle alpha m, theta becomes equal to critical angle denoted by theta c. Now substituting these values to the above equation, we get n1 cos theta c equal to n0 sin alpha m. It is taken as equation 1. Now we apply Snell's law at the second interface, that is a core cladding interface. When the light falls at this interface at an angle equal to the critical angle theta c, we take the incidence angle to be as theta c and the refraction angle to be as 90 degree in Snell's formula. So we can write the Snell's law as n21 equal to sin theta c divided by sin 90. Now the left side of the equation can be written as n2 divided by n1 as the light is travelling from the core to cladding. Denominator on the right side of the equation becomes unity as sin 90 is unity. Now taking sin theta c equal to n2 divided by n1. Now we transform sin theta c as cos theta c using the formula cos theta c equal to square root of 1 minus sin square theta c. But sin theta c equal to n2 divided by n1. So the equation becomes cos theta c equal to square root of 1 minus n2 by n1 all square. Now on simplifying we get cos theta c equal to square root of n1 square minus n2 square all divided by n1. It is taken as equation 2. We have the equation 1 and we can substitute the value of cos theta c on the LHS of equation 1 from equation 2. We get n1 multiplied by square root of n1 square minus n2 square all divided by n1 equal to n0 sin alpha m. On simplifying we get square root of n1 square minus n2 square equal to n0 sin alpha m. But as per the definition of numerical aperture, it is equal to sin alpha m. So in this equation, in place of sin alpha m, we take it as numerical aperture Na. So Na or numerical aperture which is equal to sin alpha m is equal to square root of n1 square minus n2 square all divided by n0. This is the equation for calculating the numerical aperture of an optical fiber when it is placed in a medium having refractive index n0. Now if the optic fiber is kept in air, then the value of n0 is unity. So the equation takes the form numerical aperture Na equal to square root of n1 square minus n2 square. Now we make a comparison between the numerical aperture of an optic fiber placed in air and that is placed in a medium of refractive index n0 which is greater than the value in air. From the equations, it is clear that when n0 is unity, the denominator is minimum compared to any other values of refractive index. So the numerical aperture is maximum when we place an optic fiber in air. Now when we place it in any other medium, the n0 is greater than unity. So the denominator term increases and so the numerical aperture decreases. This means the acceptance cone or the light gathering capacity is maximum for an optic fiber when it is kept in air and it decreases when we keep an optic fiber in any other medium. This is shown in the figure. Now we discuss the advantages of using optic fibers. Firstly, optical fibers have extremely low transmission loss and hence we can have much greater distance between repeater stations. Secondly, optical fibers are typically about 100 micrometer in diameter and are basically made of silica and glass. So the volume and weight is very less. Thirdly, optical fibers are robust to electromagnetic interference. So it eliminates crosstalk, which is a common problem in conventional cable communication system. And finally, it is very cheap since it is made of silica and glass, which are abundant in nature. Now we discuss the topic optical fiber transmission network. Here with the help of a block diagram, we discuss how a signal from a source is transmitted via optical fiber and we will see how this is received and reproduced to its original form. At first we see the transmitter session. This is the block diagram of the transmitter session. At the transmitter end, the analog signal from the source is first converted into digital form using an analog to digital converter, that is ADC. The output of the ADC is fed to the laser driver which converts the digital electrical signals into digital light pulses. Now for transmitting these light signals, we make use of optic fibers. So the output of the laser driver is fed to the optic fiber channel to transmit the signal. Now we will see what is happening at the receiving end. This is the block diagram of the receiving end. At the receiver end, the light signals from the optic fiber is first passed through an amplifier to compensate for the loss of energy during the travel through the optic fiber channel. The output of the amplifier is fed into decoder, where light signals are converted back into electrical signals, which is then passed through digital to analog converter, that is DAC or DAC. The output of the DAC is the original signal sent from the transmitter. This is how the original signal is reproduced at the receiver end. and the overall view of the optic fiber communication network is shown in the figure. This is the description for the working at transmitter end. This is the description for the working at transmitter end. Now we discuss about the optic fiber as a sensor. For that, we classify the fiber optic sensors as two types. One is the intrinsic sensor, where the optic fiber is used as a sensing element. The other is the extrinsic sensor, where the optic fiber is not directly used as a sensing element, but it is used as a means of relaying signals from a remote sensor to the electronics that process the signals for the sensing purpose. In the case of an intrinsic sensor, the optic fiber itself is used as a sensing element for any measurement. Measurement means the parameter that we measure. It can be temperature, pressure, etc. In the figure, we see the optic fiber used as an intrinsic sensor. Here the light is passed through the optic fiber through one end and collected from the other end. The intensity of the light received at the receiving end of the optic fiber will vary depending on the frequency of the change in the measurement or parameter on the sensing region of the optic fiber. As an example, the intensity of light varies accordingly with a change in temperature or pressure acting on the optic fiber. So we can say the variation of the parameter or measurement is modulated to the intensity of the light passing through the optic fiber. Thus the optic fiber itself acts as a sensing element and carry the modulated information in terms of light about the measurement in the intrinsic sensor. In the case of an extrinsic sensor, the optic fiber is used only as a channel to carry the light into an external transducer and back from it. The external transducer is a device that will transform the variation of the parameter of interest, for example temperature, pressure, etc., into light information. So here the optic fiber is used to carry unmodulated light into the transducer and to take back the modulated light out of the transducer for further processing. Now we discuss about the intensity modulated sensor. This is the block diagram of the intensity modulated sensor. Here the optic fiber is used as a channel to carry light into and out of the transducer that measures the measurement. So we say here optic fiber is used as an extrinsic sensor. To explain the diagram, first we use a bright source of light. It can be a laser or LED. The light from the source is carried to the transducer using optic fiber, denoted as FO. The transducer will modulate the information about the measurement, which can be temperature, pressure, etc., onto the light which is passed through it. This modulated light is carried out of the transducer using another optic fiber to the detector. The detector can be a photodiode or a phototransistor which converts the modulated light information into corresponding electrical signals. This is then used for further electronic processing to make an information that can be interpreted. The electronic processing unit can be an oscilloscope or optical spectrum analyzer. This is the explanation of the block diagram of the intensity modulated sensor. Here we discuss about the phase modulated sensor. The main parts of this sensor are shown in this figure. The parts are source, detector, 3D coupler, reference fiber arm, sensing fiber arm, transducer, and two mirrored end phase. It works based on the principle of interferometry. It can be made using different types of interferometers. Here we make use of the Michelson interferometer. So before we discuss about this device, first we try to understand about the Michelson interferometer. The Michelson interferometer consists of a light source, detector, two mirrors which are placed at 90 degree each, a beam splitter kept at 45 degree with the axis of the light source, and a detector. When we turn on the light, the incident ray falls on the beam splitter and the ray is splitted into two rays of equal amplitude. One ray travels towards the mirror 1 and the other ray travels towards the mirror 2. The distance between the two mirrors from the beam splitter is fixed to be as same, and that distance is denoted by D. Now the ray gets reflected back from mirror 1 and from mirror 2, which meets at the beam splitter and moves towards the detector. The detector measures the intensity produced by the interference produced by the two reflected rays. As the distance between the two mirrors from the beam splitter are equal, the path difference between the two reflected rays is 0. In other words, they are in phase and there is no phase difference. So we get maximum intensity due to constructive interference. Now if we fix the distance from the mirror 1 to the beam splitter as d itself for reference, and if we increase the distance of the mirror 2 from the beam splitter so that the new distance be d prime. Now when we send the incident light, it split into two and gets reflected from the mirror 1 and mirror 2 and meet at the beam splitter and travels towards the detector as we have seen earlier. But this time, as the distance d and d prime are different, there will be a path difference between the two interfering light rays at the detector. As shown in the figure, the light ray from mirror 2 will have to travel more path compared to the ray traveling to and back from mirror 1, which produces the path difference. Because of this path difference, a phase difference will be occurring between the two light rays. Based on this phase difference, the interference may be constructive or destructive, which give rise to an intensity which may be high or low or in between. This can be noted down on the detector. This is the basis of the Michelson interferometer. So in this diagram, the distance to the mirror 1 is fixed for reference. So we can say this is the reference arm, and the distance to the mirror 2 is varied. So we can say this is the sensing arm on comparison with the block diagram for the phase modulated sensor. Now we try to understand how the working principle of Michelson interferometer is used in phase modulated sensor. Here the light from the source is sent to the input of a 3D coupler. The purpose of the 3D coupler is to divide the incident light into two equal amplitude light beams, which is having a phase difference of 90° between them. It is called as 3D coupler because in decibel units half the power is 3 dB. So as this device is dividing the incident light power into two halves, each half will have half the power or 3 dB power. Now one of the output of the 3D coupler is connected to one phase of an optic fiber which is having a fixed length. It is called as the reference fiber arm as compared to the distance to the mirror 1 in Michelson interferometer. The other end of the reference fiber arm is mirrored. Now the second output from the 3D coupler is connected to one phase of another optic fiber which is having a transducer connected in series with its length. It is called as sensing fiber arm as compared to the distance to the mirror 2 in Michelson interferometer, because the transducer connected to the fiber changes its length in response to the measurement like temperature, pressure, etc. The end phase of this optic fiber is also mirrored. Initially, the length of the two fiber arms, that is the reference and the sensing fiber arm, are calibrated to give the same length. So the light that travels from the 3D coupler through the reference and the sensing fiber arm will be reflected from the mirrored end faces and combined in the 3D coupler. The resulting light is sent to the detector. Now when we use the sensor for sensing any measurement, then the transducer connected to the sensing fiber arm will change its length in accordance with the measurement. So the length of the sensing fiber arm will be different compared to the reference fiber arm, which is kept in isolation from the measurement. This will generate a path difference between the two rays reaching the 3 dB coupler from the reference and sensing fiber arms after reflection. This path difference produces a phase difference between the rays. So the intensity vary in accordance with the phase difference between the two rays from the two arms, which is related to the measurement. In other words, the variation in the measurement is modulated into the phase difference produced between the rays from the reference and the sensing fiber arm. This is then sent to the detector, which detects the variation in intensity of the phase modulated light. This is how the phase modulated sensor works. Here we discuss about the applications of optic fibers. They are used as sensors to measure or monitor displacement, pressure, temperature, flow rate, liquid level, chemical composition, etc. They are used for remote monitoring and surveillance. They are used in cable TV, CCTV, LAN, WAN, etc. They are used for signaling and decorative purposes. Intranet and internet connections are made through optical fibers. They are used as biosensors to measure and monitor many significant parameters in the human body, including temperature, blood pressure, blood flow, oxygen saturation levels, etc. They are also used in endoscopy. Now we make a comparison between single mode and multi-mode optic fiber. First we look the case of a single mode optic fiber. The simplest type of optical fiber is called single mode. It has a very thin core about 5 to 10 microns in diameter. In this type of fiber, all signals travel straight down the middle without bouncing off the edges. Cable TV, internet, telephone signals are generally carried by single mode fibers wrapped together into a large bundle. Cables like this can send information over hundreds of kilometers. This figure shows how the rays travel in a single mode and multi-mode optic fiber. Now we look the case of a multi-mode optic fiber. Each optical fiber in a multi-mode cable is about 10 times bigger than one in a single mode cable. So light beams can travel through the core by following a variety of different paths, that is multiple different modes. Multi-mode cables can send information only over relatively shorter distances and are used to link computer networks together. This is the end of part 3. Thank you for watching this RSET online video session on the topic photonics. For more lectures, please visit the link shown below.